Good afternoon, everyone. Welcome to the pre-recorded lecture for solid Earth Geophysics on 6th of November 2020. Just present my screen and then I will begin the lecture. So, in the previous class, we have been discussing about earthquake seismology, and this is where we essentially ended. We said that, a moment. We said that we introduced to you the magnitude of earthquakes, and then we said that larger the magnitude of the earthquake, we have less number of earthquake frequencies. Okay, so this is where we essentially ended the last lecture. So let's just continue with the same thing. So, in terms of energy release with respect to different magnitudes of earthquake, if we have a 2 magnitude earthquake, what we observe essentially is it's equivalent to a large query blast, uh, and the equivalent energy is given here. And then, if it is a 2.5 magnitude earthquake, it's around a moderate lightning bolt equivalent energy is given here. And then 3.5, it's like a large lightning bolt. You can see the equivalent energy. 4.5 average tornado, 6 Hiroshima atomic bomb, 7 magnitude earthquake, largest nuclear test, 7.7 magnitude earthquake, Mount St. Helens eruption, 8.5 is equivalent to Krakatoa eruption, and 9.5 is the Chilean earthquake 1960. Okay, that's the largest earthquake that happened in human history. Okay, and you can see, of course, that the energy essentially exponentially increases, as we said that per magnitude, 1 unit of magnitude increase is equivalent to 32 times energy, more or less, roughly 32 times energy release. Okay, and they are some of the natural analogies that you can relate the amount of energy that will be released for each equivalent earthquake episodes. Okay. So here are some 10 largest earthquakes that happened in the world since 1900. The biggest one, as I said, Chilean earthquake, 22nd May 1960, magnitude 9.5, deaths around more than 5,000. Then Alaskan earthquake, 2.28 March 1964, magnitude around 9.2. But you see the number of deaths is significantly less, only 131. So you can imagine why, simply because Chile is a very highly populated country, but Alaska did not really have a lot of population. So hence the number of deaths were also less. Russia, 4th November 1952, there were no person died. Ecuador, 8.8, more than 1,000 people died. Then again in Alaska, then Kuril Island, Alaska, India, 15th August 1950, 8.6 magnitude earthquake, around 1,530 people died. Chilean earthquake, 11th November 1992, 8.6 magnitude, more than 100 people died. Indonesia, 1st February 1938, 8.5 magnitude earthquake. Nobody died. Okay. So, how many people actually, the casualties, the number of casualties is not exactly always directly related to the magnitude of the earthquake. It also depends on whether it is happening in a desert or in a mountain or in a city. If it happens in a city, of course, you know, it essentially can kill a lot of people. So these are 10 world earthquakes causing the largest number of fatalities. You can see the Shanxi earthquake, then the uh, Antioch earthquake in Syria, then another in China, Azerbaijan, China, Iran, Japan, Syria, Italy. And you can see how many people actually lost their lives during these earthquakes, right? So, yeah, it can be really, really traumatic. Now, this is what I was talking about in the last class, that the magnitude of earthquake is actually a fractal quantity. Now, what you can see here in the y-axis, the frequency of earthquakes is plotted in the log scale, and then the magnitude of the earthquake is plotted in the x-axis, right? Now, what is the use of such diagram? I'll just explain that to you. Now, let me just take a snip, and then I will draw it on it. Now it's happening. Here is the snipping tool. All right. So you can see here what has been done here is, you know, so this is in the x-axis, I have uh, magnitude of earthquake, and in the y-axis, their corresponding frequencies, which are plotted, right? And then this is plotted in the log scale. Okay, so what it essentially means that I will have to look through the record of the earthquakes, okay, and then I have to make like a chart, like between maybe from say around 1800, between 1800 to maybe you know 2000, yeah, between 1800 and 2000, around 200 years. Okay, I am looking at the data. And what type of data I'm looking? I'm looking, say, for example, between 2 to 4 magnitudes, or no, maybe even less. Between 2 to 3 magnitude earthquake, maybe I had 1,000 earthquakes. Okay, between 3 to 4, I had maybe 500 earthquakes. Okay, between 4 to 5, maybe I had 200 earthquakes. Between 5 to 6, I had maybe 100 earthquakes. 6 to 7, yeah, I had 50 earthquakes. Okay. 7 to 8, maybe I had 10 earthquakes, like that. Okay. So what I would do, I would plot in my x-axis the magnitudes. Okay. And then in the y-axis, in the log scale, I'll plot their frequencies, this number, right? Then what I will observe that I have like a variation like this, right? Now, so if I have a variation like that, I can actually fit a linear scale through it. I can fit a linear scale through it, and that linear scale can be expressed is equals to y is equals to mx plus c. So here log n, of course, is equals to c, which is the intercept, of course, minus, because it has a negative slope, m into magnitude. Sorry, we can put it as b into magnitude. N equals to p minus p into magnitude. We can put it like that, right? Now, of course, what is the advantage of such data? You can actually extrapolate these data, and it will touch. If I just linearly extrapolate that data, it will touch to a particular point. Okay? And then maybe I can draw another two lines. Can draw another two lines which actually cover the whole set of data. And those two also will touch in these 2 points, right? Now, they can provide us a futuristic estimate of what is the maximum magnitude of earthquake is possible in that area. Okay, maybe this comes around 7, and this comes around 8. Okay, and this is may around 7.5. Okay, so I can say that most likely in future the highest magnitude of earthquake that can happen here would vary between 7 and 8, and most likely it will be around the 7.5 magnitude earthquake, which is most likely. Now, does that always happen? Now, if we look at this particular data with the same logic, I can draw a line here. I can also draw a line, somewhere here. Okay, so I can see that the maximum magnitude of earthquake in this area could have been 5, and another maybe 4.3 or 4. But then we can already see that this doesn't did not validate in this particular area. It did not validate the statistics. We had a earthquake which is of magnitude 6. But this is, I mean, if you don't have anything, I mean, earthquakes are so unpredictable that if you don't have anything, this is one of the ways by which you can have a rough estimate that you know that the maximum magnitude of earthquake could be between 4 to 5, but it doesn't always work. That is also something you have to remember, but it can work. It has worked in many places. So we actually trust the factual nature of earthquake, and this type of analysis can be used to actually predict what sort of maximum magnitude of earthquake could have been there. Okay? Now let's continue. So the thing that we have been discussing is called observational seismology on macro seismology. So macro seismology deals with the effects of earthquake on humans, animals, objects, and its surroundings. The data are collected by the field trips into the shaken area, and by questionnaires are sent to people. Actually, they can talk about the intensity that they felt. The effects are then expressed as earthquake intensity at each of the studied places. Okay, but this is a subjective method. Now, what sort of classification that they propose? European macroseismic scale, as per European macroseismic scale, Roman 1 stands for something which is not felt. Roman 2 stands for which is scarcely felt. Roman 3 stands for which is weak. Roman 4 is largely observed. Roman 5 is strong. Okay, and then they have their corresponding description, which you can read from the slide itself. Say, for example, the largely observed earthquakes are felt indoors by many people, outdoors by very few, and few people are awakened. Actually, strong earthquakes, the earthquake is felt indoor by most, outdoors by few. Many sleeping people awake. Few people runs outdoors. Buildings tremble throughout. Okay, so these are like more subjective way of expressing the strength of an earthquake. Slightly damaging 6, damaging 7, heavily damaging has a scale of 8. So heavily damaging means furnitures may be overturned or toppled. Many ordinary buildings suffer damage. Chimneys fall. Large cracks appear in walls, and a few buildings may partially collapse. And destructive monuments and columns falls or twisted. Okay, that has a scale of 9. 10 is very destructive. All many ordinary buildings collapse. Devastating is 11. Most ordinary buildings collapse, and 12 has the highest scale, completely devastating. Practically all structures above and below the ground are heavily damaged or destroyed. Okay? Now, with that sort of intensity in mind, you can prepare something called isoseismal map. Isoseismal map means a contour map which actually plots the intensity of earthquake. For example, you can see here this is maximum intensity earthquake. So just approximately epicentral intensity is I0 is equals to magnitude plus 2. Okay. Now, don't confuse yourself with intensity and magnitude. Okay. So, intensity is essentially more subjective, which is uh, felt by people. Okay. So, one earthquake has just one magnitude but can have many intensities. So, for example, an earthquake which is, say, for example, a 6 magnitude earthquake. Close to the epicenter of the earthquake will be having more intensity than something maybe 1,000 kilometers away from it. But at 1,000 kilometers away from it, it will still have a magnitude of 6, but the intensity will decrease significantly, right? So there will be a plane, there will be an area. For example, like here you can see this is 8. This is in the 8 intensity scale, 7 intensity scale, 6 intensity scale, 6 intensity contour, 5 intensity contour, and 4 intensity contour. Maybe after 4 intensity contour, as per here we can see, it doesn't really matter. See, after 4 it is quite weak, so it doesn't perhaps matter to actually contour it anymore. So from 8 to 4, here you feel the earthquake, but with different intensity. Although the magnitude remains the same. Magnitude is more of a more of a objective sort of description of the earthquake, where more science is involved. But the intensity is more like how human being felt it. If you are closer to the earthquake epicenter, of course you will feel it more. If you are away from the earthquake epicenter, you will feel it less. And then but intensity is more practical of a use. For example, if I have a 6 magnitude earthquake happening in maybe 8 magnitude earthquake happening in Chile, and I'm sitting in Bhopal, although it is an 8 magnitude earthquake, does it really matter about the safety and security of Bhopal? Perhaps not. But what essentially matters, maybe a 4 magnitude earthquake that is happening, very close, maybe in Sachi, maybe that would harm Bhopal more than something which is of higher magnitude but happening at a distant place. Okay, so hence the intensity is more practical of have more practical use than magnitude, because it actually mm, you know um, changes our perception about how to deal with it. Okay. Now, this particular topic I will end with a note that earthquakes do not really kill people. Earthquakes are harmless simply because that's just the shake of the ground. If you just stand on a empty field, and if there is an 8 magnitude earthquake, maybe there will be some, you might fall down, and you might break your leg, and that's about it. Nothing else will happen. Which actually, what kills people is the large buildings that we essentially build. Higher the building, weaker the building, we actually put ourselves into more threat. Okay, so the high rises are really not very optimum to be built in an area which is earthquake prone. Okay, so it's not the earthquakes by themselves that kill people. What kills people are the buildings, right? So there, with that in mind, there is another subject which is actually built up, which is called engineering seismology, which is a branch of civil engineering, which essentially and earthquake engineering, which actually talks about building earthquake resistant houses. And there are plenty of techniques which we can discuss maybe some other time at leisure, how to make your buildings earthquake resistant. Okay, there are standard procedures everywhere. Okay, so yeah, so the moral of the story is, it's not earthquakes that kill people, it's your buildings, right? So you have to make your buildings in such a way, so your town planning should be in such a way that you can actually avoid this horrific natural disaster. Yeah. So now I would like to talk about another important topic, which is called focal plane mechanism. Okay. And that is a bit more technical around describing earthquakes. As a geophysicist, you must know what focal plane mechanisms or fault plane solutions are. Okay, let me just put it in the presentation mode. Then we will begin talking about it. Okay. So this particular uh, technique that we are going to discuss has different names. So it is called fault plane solution, focal plane mechanism, fault plane mechanism. These are this has different names by which you describe this particular process. Okay? And this is also called creating beach ball diagrams. Yeah. So essentially, depending on the type of earthquake, we are going to create some sort of diagrams. Okay. So depending on the type of the earthquake, we are going to create some sort of diagrams that would represent the origin of the earthquake. So we, in this particular part of the lecture, what we are going to learn is how to prepare these beach ball diagrams, and these beach ball diagrams would tell us about the geometry and the mechanism of the fault which is responsible for the earthquake in a simple diagram. Okay. So beach ball diagrams are simple diagrams which are made to demonstrate the geometry and mechanism of the faulting which is responsible for the earthquake. So generally, from the moment tensor, which is more general, but originally calculated using first motion, done here, we illustrate the concept. We will explain what first motion is all about, what is moment tensor is all about in a moment. Okay. Now we know that there are three types of faulting by which earthquakes can form. The first one is called strike slip, where the individual fault blocks actually slide past each other. The second one is called normal fault. Okay. And normal fault is related to normal stress regime. Okay, it's called normal fault. Why it is called normal fault? Because you know before we say why it is called normal fault, we have to define two more things. One we call as the hanging wall of a fault, and foot wall of a fault. Okay. Now you can see here that this is my fault plane, right? This is my fault plane. And this is the strike of the fault. And the direction perpendicular to the strike of the fault. So this is the strike of the fault. And this is the line, the direction perpendicular to the strike of the fault is called dip direction. Okay. So the block which is towards the dip direction of a fault, the block which is towards the dip direction of a fault is called an hanging wall, and the block which is opposite to the dip direction of a fault is called a foot wall. So with that analogy, in this particular example, A is my foot wall and B is my hanging wall. Okay? So a normal fault is a fault where hanging wall moves down. A normal fault is a fault where hanging wall moves down, as you can see with respect to the foot wall. Okay, and in a normal fault, of course, a normal stress regime prevails where S V is maximum, more than S capital H, more than S small h. Right? Now, in a thrust fault, of course, which one would be my hanging wall? Which one would be my foot wall? If this is A, this is B. So of course, with the same logic, this is the fault plane, and the fault plane leads towards this direction, right? And this is the strike of the fault plane. It's perpendicular, right? Now, B then will be my hanging wall, and A will be my footwall. Okay? And in case of a thrust fault, what we observe that B actually moves up with respect to the B actually moves up with respect to the with respect to A. So hanging wall moves up with respect to footwall, and that is what we call a thrust fault. And for thrust fault, we do generally see reverse stress regime, and reverse stress regime is S capital H is more than S small h more than S V. Okay, SV is the smallest. And in a strike slip stress regime, there are no such hanging wall and footwall because nothing goes up or down, and the deep of the fault is 90 degree. So for a 100% strike slip fault, you don't have any sort of hanging wall or footwall. And here we see that the stress regime is strike slip stress regime. So where S capital H is more than SV more than S small h, right? So SV is intermediate. Okay. And then, if a earthquake is formed by a strike slip fault, it is represented by a diagram which looks like this. This is a typical beach ball diagram for a strike slip. Uh, for an earthquake which is formed by a strike slip fault, how this diagram is created, we will just discuss in a moment. But for the time being, remember this type of diagram where I have I have a circle, and then I have, of course, it cross cuts each other. There are two pluses, two minuses. We will explain what are they. Okay, this is typically associated with a strike slip fault. For a normal fault, this is how a beach ball diagram looks like, and for the thrust fault, this is how a beach ball diagram looks like. Okay. Now, of course, there is something else what we have to understand, and which we talked about before, of course, in your introduction to earth science classes. We are going to use stereographic projection for the preparation of visual diagrams. Okay. So if you have forgotten about stereographic projection, please make sure that you refresh yourself about stereographic projection. But that is something that we are going to use in this particular lecture. Okay. If you have forgot it, please make sure you refresh what is a stereographic projection. Now, this is fine. This is a typical picture of a stereographic projection. Any plane, any plane is actually designated by great circles. Any plane is designated by great circle. Okay, and you can see here the deep and the strike of any plane can be described by the by a great circle. So where here we have drawn a particular plane which has a particular fault plane which has a strike of 109 degree and deep of 55 degree towards southwest. Okay, and this is the corresponding plane associated with that particular fault plane. Okay, I have taught you, I myself have taught you this particular stereographic projection in your pre-major classes. So if you have forgot, you have to refresh yourself what exactly it is. Okay, so a plane is represented by a line in case of a stereographic projection. Okay, similarly, a line a line is represented by a point. Okay, so in this particular example, I am plotting a point which has a I'm plotting a point which has a trend of 239 degree and a plunge of 43 degree. Okay, and that point would come here. Okay, and I have explained how such points are plotted. Okay, so make sure that you learn that part as well. So that's what is all about stereographic projection. You can plot a point, and you can plot a plane, and you can also plot the pitch of a point. You can also plot the pitch of a particular line. We have explained what is pitch. Pitch is the angle between the strike of a plane and the angle and that particular line. And you can see here there is this particular line this blue line which is sitting on this particular plane, which has a pitch of 20 degree, and that pitch can be plotted here. Okay? You need to refresh it as well. So we talked about what is uh, deep strike, rake, or rake or pitch. Okay, we talked about it: deep strike, rake, and pitch. So before I think in the next class, then I will start talking about uh, actual building of these beach ball diagrams. But what I want you to do over the weekend and till next Friday, I mean next class, which would be on next Wednesday, okay, to actually refresh yourself with the stereographic projection technique, so that we can start afresh with the plotting of visual diagrams. Okay, so I'll end the lecture today here, and I will see you on Wednesday. Thank you.